and welcome to this manufacturing process technology part 2 module 10. We had finished the microelectronic processes in the earlier module where we talked in length about the different sort of alternate processes which were first generation non-traditional processes, particularly using silicon as borrowed from microelectronics to fabricate micro machine structures or small structures. Today we are going to again discuss a very important form of non-traditional or advanced machining, which is related to the mechanical version of the machining, where there are use of abrasive particles, and typically machining is carried out by throwing such abrasive particles on the surfaces and initiating the formation of cracks and the propagation of cracks. And so therefore such processes are more amenable to brittle materials like ceramics or glasses in the industry, but not essentially limited to them. You also use them for metals, you can use them for a variety of other different materials. So there is a impact that is being tailored in a manner so that there is a crack which formulates on a surface, and that's how such processes are categorized. So let's look into this process of abrasive jet machining, or AJM. Okay. So in this particular process, the material removal, as I told you, takes place due to impingement of fine abrasive particles. Let's say suppose there is a nozzle here, and this nozzle is made up of something which is very hard material like tungsten carbide, which doesn't get so easily influenced by the continuous abrasion provided by the flowing abrasive particles. There is a high speed jet of air which has hopped in abrasive particles by a system which we will describe when we talk about the machinery, and it impinges, or it basically formulates air abrasive mix which flows out from this nozzle at a high velocity of almost as high as 150 to 300 meter per second. So therefore whenever this high pressure jet is directed to go from a nozzle into an open atmosphere, there is some kind of an expansion to the jet which happens, although the momentum is too high, and it gets carried for certain duration as as of the same size of jet without much expansion, but after a while it starts expanding, and if we could capture that jet prior to its energy starts getting dissipated because of the drag provided by the atmospheric air, I should be able to write with that jet on a top of a surface, because it would impact or it would create a situation where the grains are going to impact and create dislodgement of the material. Okay, so let's say we take the substrate quite close, about of the level of about 800 microns to this particular abrasive jet. So still the jet has not lost enough power because of the drag and other issues provided by the atmospheric pressure, and so therefore it's it produces some kind of a zone where there is crack formulation, because there is a continuity of these abrasive particles, and then if you can proceed the nozzle towards the workpiece, then the zone gets expanded. So you can have different depths of cut formulated as the nozzle approaches this particular region, up to an extent that the nozzle doesn't start touching the surface that is in question. So the abrasive particles are typically of about 0.025 mm diameter, and the air discharges at a pressure of several atmospheres. So that's how the nozzle and workpiece dynamics is there in this abrasive jet machining. So as far as the mechanics of the AJM process goes, the abrasive particle, this is for example a sharp abrasive particle with various edges and corners. So it impinges on the work surface at a high velocity, and this impact causes a tiny brittle fracture. You can see that corresponding to the shape of this abrasive particle, there has been a cavity formulated because there was a sudden fracture of this particular material, and the following sort of flowing air or gas which is actually there with the abrasive, which is responsible for flowing this abrasive, it carries away the dislodged small part. So you have a crack formulated in this zone, and whatever comes out, this chip is carried away by the air which is flowing along with the abrasive grain. So that's how you do the actual material removal in case of the abrasive jet machining. So, the process is more suitable when work material is brittle and fragile. So, as I told you that process was generated because there were requirements in the ceramic industry or the glass industry to sort of use a process. So, in fact, the AJM, the need for AJM was sort of felt by the industry, and the process was taken up by the industry because of the advent of ceramics or such brittle materials. And obviously, although there is a possibility of applying this to many systems including metal, etc., the highest efficiency would come when we are talking about brittle and fragile materials. So, a model for material removal has been proposed for this AJM process by Sarkar and Pandey in 1980, which talks about relating this material removal rate to variety of process parameters like number of abrasive particles impacting per unit time, mean diameter of the abrasive grain, d the velocity of the abrasive grains, v with which they are impacting on the surface, the density of the abrasive material, and then also the hardness of the work material and some constant, experimental constant which comes up. So, basically you can think of the MRR or the material removal rate to be proportional to the cube of the diameter, proportional again to 1.5 power of the velocity of the impacting grain, and also proportional to the number of abrasive particles impacting per unit time. So, intuitively it makes sense why we should go in this manner to generate the MRR. So, the process parameters which are of importance here are obviously evaluated by judging the material removal rate or the geometry of the cut or even the roughness of the surface that has been produced and the rate of nozzle wear. And the major parameters which control these quantities are the composition, strength, size and mass flow rate of the abrasive, that is the main cause of the material removal, and also the composition, pressure and velocity of the gas which is flowing or which is responsible for flowing this abrasive at that high energy of impact or momentum delivery. Also there is a sort of a good relation between the nozzle geometry, which matters a lot to generate the overall shape and size of the cut or even the surface roughness, the MRR, and things like distance from an inclination of the workpiece with respect to the nozzle is also a very important property along with the nozzle material for determining some of these process characteristics. So, let us look at some of these parameters and how the variation of these parameters would result in the change in the process characteristics. So, the first study that has been made is that if we really change the mass flow rate of the abrasive particle by changing the pressure and the flow rate of the gas. So, the first important property or first important parameter which we talked about is really the abrasive, and let us look at how it really affects the process characteristics. So, there are mainly two types of abrasives which are used in the AJM process. They are aluminum oxide and silicon carbide. The grains have a diameter of almost about 10 to 50 microns. They are readily kind of available. So, also for a good wear action on the surface concerned for the machining, the abrasive grain should have very sharp edges, and the reuse of the abrasive powder is normally not recommended because of a decrease of cutting capacity and clogging of the nozzle orifices due to contamination. So, the mass flow rate of the abrasive particles depends on the pressure and the flow rate of the gas. So, generally because there is a tendency of metal flakes or the workpiece flakes to come with the flowing air and also the thrown up abrasive into the collecting pit corresponding to all these different abrasive grains. In fact, this is done in a large chamber where whatever is bounced off the surface in terms of abrasive grains falls on the base of the chamber. So, obviously if you want to if it is not a metal that you are cutting and you want to separate, it becomes a little hard to separate, and so therefore there is always a sort of a clogging which happens of nozzles or various other portions of the machine. One of the reasons why it is not very useful to allow the reuse of the abrasive powder. So, if we look at the mixing ratio, which is actually the mass fraction of the abrasive present in the air, there is an optimum mixing ratio over which the MRR would be the highest. Obviously, intuitively also, if we look at that, if the number of abrasives per unit volume of the air has increased, there is going to be cross grain collision, which happens and which kind of jeopardizes the momentum that the grains would formulate before hitting the surface. So, therefore, it has to be an optimum loading for the grains to have enough mean free path to develop that kind of impact which is able to create brittle fracture. So, there is obviously a certain point below which, even if the abrasive particle is loaded, it means that not enough abrasive particles is there, and above which it is loaded, there is a sort of a cross collision between the grains which would jeopardize their momentum. So, there is an optimum best of the mixing ratio. We will in fact do some problem examples related to calculation of the mass fraction of such a abrasive jet machining process. And the other issue is that when the mass flow rate of the abrasive increases, the material removal also sort of increases, but this is again subjected to an optimum best, because it should not just completely. So, if supposing the mixing ratio is the same, and if you keep on adding the impact or hitting you keep on flowing the air abrasive mixture and hitting on the surface, so higher is that abrasive mass flow rate at a certain mixing ratio, the higher would be the material removal. So, obviously, the impact keeps on increasing with the velocity, as you can see in this particular case. So, if supposing the mass flow rate is lower, the impact would be lower. If the mass flow rate is higher, the impact would be higher, and so that results in distinguished or differentiated material removal rates. So, typically you should be able to use the higher mass flow rates, but that does not mean we can keep on going on the higher side, because it deteriorates the nozzle life, and that is a very critical issue in abrasive machining, that if we just simply wanted to flow at higher and higher velocities, there may be erosion of the nozzle at a much faster rate, and the nozzle may deteriorate, and you may need to change nozzles quickly. So, there is obviously a trade off between maintaining the quality of the nozzle and maintaining the higher amount of MRR in a material removal flow or material removal process related to the AJM. The other important aspect is the gas that is being used. So, obviously, the pressure ranges that are normally employed in the AJM process is between 0.2 to 1 Newton per millimeter square. So, this is a very high level of pressure that is being used to create this jet or create this velocity, and the composition of the gas is also having a great impact on the MRR, and so is the velocity of the gas, for obvious reasons, that higher velocity means higher momentum delivery, and the composition should not be typically something which may create some kind of a. So, the composition in a way is more responsible for the economics of the process, because obviously if you were to use different, first of all, it should not be hazardous. The gas that you are using should be operator friendly. That is a very important aspect. The other aspect is that it should not have its own corroding effect on the material that is being braided away, because obviously if you are using the gas for that purpose, you have to have a sealed environment to flow all that, and normally these machines are not really sealed, they are quite open to atmosphere, and so we need to be very careful about choosing the composition of the gas there. The nozzle is again one of the most vital elements in controlling the process characteristics, and as I told you, the nozzle material should be typically very hard, and hardness is needed because you are flowing abrasives continuously round the clock through that nozzle, and obviously the nozzle gets deteriorated in terms of its shape and size, and if it gets deteriorated, then the distribution of impact which would otherwise be there on the workpiece surface as a Gaussian, with the central particles being driven at the highest axial velocity and the side particles or particles emanating from the side of the nozzle having lower velocity, okay, that changes completely because of the the change in the or deformation in the total cross sectional area of the nozzle. So normally very hard materials like tungsten carbide or sapphire are used for generating these nozzles, and they have average lifetimes varying between 12 to 30 hours and approximately 300 hours for sapphire. It's a very high lifetime that we are talking about when we use sapphire nozzles, but they are actually very expensive as well. So for a normal operation of cross sectional area, for a normal operation of the AJM, the cross sectional area of the orifice that can be used varies between typically 0.05 to 0.2 mm square, and there can be also different shapes of the cross section, including a circular nozzle, rectangular nozzle, so on and so forth. But you do have to from time to time look at the nozzle shape and size and determine whether it is suitable for carrying out the machining operation before the start of such an operation. The other important factor is the nozzle tip distance, which is very important in case of all the abrasive throw processes, whether it is WJM or AJM or WAJM. So these are in terms of these are also better known as the standoff distance between the nozzle and the workpiece. And obviously, if I look at the problem intuitively again, that if the nozzle were too close to the workpiece, the amount of time that the abrasive would need to get thrown out at a certain velocity and at a certain acceleration to attain a full velocity would be very less. Okay, so the nozzle tip distance, to an extent, that the velocity should be higher with distance. Obviously, the velocity square is a function of is directly proportional to acceleration and the distance traveled. V square equal to twice AS. So up to a certain distance, the material flow rate would increase because the velocity is going to go higher. But we should think about it that there is an aspect of divergence of the gas jet that has been emanated from that nozzle into the atmosphere, and this divergence also is because there is an air drag which is offered to the particle in the reverse direction, because of which there is a change in the momentum. So the velocity does not keep on changing or increasing almost indefinitely, but after a certain distance has been traversed and the jet is a little bit farther away from the workpiece, there is a huge atmospheric drag issue which would come to take place. So for a certain amount of distances, between this critical distance where the velocity would start to fall down and this let us say this acceleration effect, there is going to be a plateauing, that there is a trade off between the increase because of acceleration and the reduction because of the drag, and beyond which the drag would start dominating, so that the material removal rate would flow down. So if I really plotted the MRR with respect to the nozzle tip distance for the first few paces of distances, between the workpiece and the nozzle, the MRR would increase. Then there is again a region of plateauing where there is a balance or a trade off between the accelerative component and the drag component of as faced by the particle, and then obviously the drag would start dominating, bringing down the MRR during this particular set of nozzle distances. So obviously there is a trade off that has to be balanced, and it has to be set up at the start of any process for obtaining the nozzle tip distance. Also, it is mind you a very important, it is very important to look at the cross sectional area of the nozzle before start of the process, because the NTD may change because of a change in the cross sectional area. So typically the NTD or the nozzle tip distance is also responsible for the overall shape of the feature which is being created because of this brittle fracture effect. And as you can see that if you go down and the nozzle gets on diverging, the aspect ratio of the impression that is being made also changes quite a bit. The initially at the very beginning of the process, when the nozzle is closer by, the aspect ratio probably is higher, and the depth attained of the brittle fracture process is much larger in comparison to the width, but slowly the width increases and the depth reduces. So it comes to almost unit aspect ratio when we talk about increasing the nozzle tip distance from the workpiece surface. So the nozzle tip distance or the standoff distance is a critical parameter in AJM, and not only affects the MRR from the work surface, but also the shape and size of the cavity produced. And as shown in the figure, the velocity of the abrasive particles impinging on the work surface increases due to their acceleration after they leave the nozzle. This increases the MRR. With a further increase in NTD, and the velocity reduces due to the drag of the atmosphere, which initially checks the increase in the MRR, then decreases it. So that's what the curve here describes. And some of the features which actually have been done realistically in a actual AJM process have been listed here for various NTD values varying between 2 and 20 mm. And as you can see here that during the 2 mm nozzle tip distance, the aspect ratio is quite high, but it keeps on changing and the depth keeps on reducing, whereas the width keeps on increasing as you're changing the nozzle tip distance all the way to about 20 mm. So that is a very important component of the AJM process. The other important aspect is the mixing and the mass ratio. Obviously, mixing ratio is highly influential as far as the MRR goes. It's the volume flow rate of the abrasive particles per unit, the volume flow rate of the carrier gas. And in place of M, the mass ratio, in place of this maximum ratio, the the mixing ratio, the mass ratio M is really determined as the mass of the abrasive by the mass of the abrasive plus carrier gas. So there must be a relationship between the alpha and M if we can just talk about densities and volumes. Let's look at some of the practical problems, numerical problems which can be important from an AJM standpoint. So during an AJM process, the mixing ratio that is used is about 0.2. We have to calculate the mass ratio if the ratio of the density of abrasives and density of the carrier gas has been given to be equal to about 20. So we know that the mixing ratio in this case is the volume flow rates of the abrasive and the gas, and you can call this M, okay, and the mass ratio from earlier definition alpha equals the mass flow rate of the abrasive grain plus that of the abrasive plus the gas which is used, which I can always write as rho A, that is density of the abrasive times of the volume flow rate of the abrasive divided by the density of the abrasive times the volume flow rate of the abrasive plus density of the gas volume flow rate of the gas. Okay, so this is actually the mass ratio between the abrasive and the abrasive plus gas. And if I wanted to just simply put this or convert this in terms of what I had for the mass ratio or mixing ratio given to be 0.2 in this particular case, then I would just like to invert this by making this 1 by alpha. So 1 by alpha or inverse of mass ratio is again 1 plus rho g by rho A Vg dot by Va dot, and if I substitute the value here, the density of the carrier gas, the density of the abrasive and the carrier gas is sort of given to be 20. So that of the gas to the abrasive grains is 1 by 20 times of the inverse of the mass ratio 0.12. So the alpha comes out to be equal to about 80 in this particular case. So I can calculate the mass ratio given the density values of the abrasive and the carrier gas and also the mixing ratio. So such problems are very commonplace in AJM when you will have to calculate these for doing such a process. With this, I would like to sort of end this particular module, but in the next module we will take up some more examples of the AJM and do another mechanical process which is also known as the ultrasonic machining. Till then, goodbye. Thank you.